Today we're going to talk about audio, but before we do, I feel like we need to give some closure to our discussion about the PPO lab. So I have weighed various options, and it felt like to me that the option that seems to be the best thing is to make this lab worth more. The reason for that is twofold. One, if you've already done it, then awesome, bonus points for you. Two, if you were counting on extra points being available, you have the chance to get those points, and you've had lots of time to work on this, you have more time to work on it. But I wanted to I wanted to know how you felt about it. Just wanted to make sure I'm not making a really wrong-headed decision here. Yeah.
How does this relate to the due date? Like what's
Still Saturday.
Okay, the due date's officially Saturday.
Saturday, yes. This Saturday. So are we cool with that?
How much will it be worth?
So I was imagining doubling it. So because we spent a lot of time on it, and we had a lot of time to work on it, and then I just felt like I just want to cancel the final two labs, but I wanted to just outright cancel them, and I don't want you guys working in more labs at this point in this semester. You just all need to be focusing on your final projects entirely. So that would be essentially one more lab's worth of credit available to those that get the points. And if you've already done the lab, then that's great.
Would it be bad to put the due date back one more Saturday in that case?
I don't mind. How do you guys? Is that okay? So are you guys? Is everybody cool if we move it back one more date? So we'll double the value of the lab, but move it back so you can continue to work on it.
So that means that we will have no more labs.
And then no more labs. Thought?
Is it the same grading scale? Do we have to do anything different?
Same grading scale.
Okay.
And as long as ours was like we could show that it was learning and getting better at both times, then
Right.
we're
Yeah, I mean, that was the step. Does this sound fair? So I want this to be a useful, good learning experience for you. I know a lot of you have put a lot of time into it, and I want that time to be rewarded. So, and if you were if you were just intellectually brilliant and happened to get it done like in 2 hours, then good job. You get lots of points for it. So hopefully that's a win-win for everyone. Yeah.
Just for the labs that are getting just started, are you still post what they put?
Yeah, I'll try to post it. Yep.
This is a completely different question, but with the final project, when is it due?
Oh yeah. So I think the spec says the last day of finals. Is that right?
I mean, our final is the last day of classes, so that would work either way.
I mean, there's no other option. We're not doing presentations. Stand by. So I'm pretty sure. Okay, so Thursday, December 13th is the last day of classes. That's when all of your labs are due. Any late labs have to be turned in by that point. I'm not allowed to accept late work after that point. The only reason we kind of get away with it for final projects is because that's in the middle of the final exam. But yeah, I think the last day of finals is when your final project is due. What is that? Actually, we have to look that up.
I think it's the next Thursday. 20th.
Somewhere. Okay, Thursday, December 20th. Thursday, December 20th, 5:59 p.m. That is the due date for your final project. Stand by. So let's just make sure. Sorry, I'm doing this in real time. Let's just make sure that that is correct here. Final project. Oh, okay, yeah, this is wrong. So we want this to be Thursday, December 20th at 5:59 p.m. Right? Is that right? Okay, good. All right. Great. Great, so let's have some fun with the audio today. Oh, a couple questions, go ahead.
Sorry.
That's right. Training is not included.
Okay.
So-
Because there were some things in the spec
Yeah.
that made it seem like it was.
What I mean by that, and I understand. So clear, I hope this is obvious, but like clearly, if you kick off a 6-hour training run and then like go to bed and then wake up and like 6 hours later, like check it out, you are not allowed to count 6 hours worth of time. I hope we're all clear on that. What I meant by training is sometimes when you're like getting training going, you're like starting training and then you're stopping it, and then you're starting it and you have a bug, so like, and you're just like, I mean, it doesn't, it's like, you're not developing topology, you're not collecting data, it's like you're training, but it's not the autonomous time, right? Okay, yeah. Hopefully that's clear.
So like,
Scott?
Oh, ours is more related on some.
Okay.
so like that's, okay, so like that debugging, miscellaneous training sets, run it for like 2 minutes, and you're trying to mess with other stuff. That's the training time that doesn't count towards your 20 hours?
Oh, no, that's good.
Or like, okay, so there's the 20 hours, so 35 hours total, and 20 hours has to be, I'm confused about how it relates to the 20 hour thing.
So I would consider all of that debugging and development. So as distinct from, the 3 big categories are reading/research, data collection, data preparation, data generation, data cleaning, data massaging, data scrubbing, data normalization, data, whatever. It has the word data in it, it goes in bucket number 2. And then there's the time that I hope that, where I want you to spend most of your time, which is building the network, testing the network, visualizing it. Because what's going to happen is you're going to try, and there's going to be a lot of, what I hope is the science of your project, where you're testing different topologies. You're going to say, does batch, like I'm overfitting. Well, like first you'll try something, and you'll be like, did it work? I don't know. And so you'll build some graphs, and the graphs will tell you, oh, I'm overfitting. It's like, okay, I'm overfitting. So then what? I should try batch normalization. So then you're going to recode your topology, and you're going to try batch normalization. And you're going to try to run it, and it's going to crash. You're like, okay, you go back and you fix it. And then it'll work. And then you'll go get a burger. And then you come back. And then you'll analyze the results. And you can count all of that time except for the burger time. Okay? Unless it's a working, right. Coding with one hand, Big Mac in the other, like that's fine too.
So now I have a follow-up question. So I've heard that at least 20 hours has to be spent on the actual
Right.
machine learning side
Right.
of it. Is
Right.
there any minimum time requirements for data collection or things like that?
There's no minimums, no. In fact, your project could be that you spend all of your time on,
Okay.
so there's only maximums. Sorry, the only maximums you're allowed to count. You are welcome to spend more than 5 hours researching. It's just that you can't count that as part of your log.
Got it. Okay. And then my unrelated question was just simply about TA schedules. Like, one, I heard earlier, we're not going to have any more labs after PTO.
Right.
And so, with that combined with the fact that we're coming up on finals, I know the TA schedules are probably going to be a little bit crazy, just like ours. Do you mind asking them to just look at their hours and see if there's any changes that need to happen and post those as needed?
I will ask. Yeah.
Thanks.
I'll ask. Okay, I don't have a pen. Okay, any other questions? Good, okay. Great, then let's talk about audio. So today we're going to talk about wavenets. So wavenets are kind of this really cool thing that Google DeepMind came out with. We're going to talk today about speech synthesis. So how do we use deep neural nets to generate realistic sounding voices? How many of you have seen the Google Duplex demo video? Okay, a couple of you. Not that many though. So I was wondering if we would show it. You guys seen this? Okay, so we're going to watch this for just a second. Because I feel like this is the culmination of a lot of efforts, and I think maybe a bit of a pointer to the future. So this is the Google CEO, and I can never say his name. Pichai? Yeah, anyway. So he's gonna introduce this Google Duplex thing. So let me make sure we scroll past all the boring stuff.
It's 70 seconds in.
Yeah.
I may have used this in a presentation earlier this week.
Seamlessly in the background for you. So what you're going to hear is the Google Assistant actually calling a real salon to schedule the appointment for you. Let's listen.
How can I help you? Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd. Sure, give me 1 second. Sure, what time are you looking for around? At 12 p.m. We do not have a 12 p.m. available. The closest we have to that is a 1:15. Do you have anything between 10 a.m. and 12 p.m.? Depending on what service she would like, what service is she looking for? Just a woman's haircut for now? Okay, we have at 10 o'clock. 10 a.m. is fine. Okay, what's your first name? The first name is Lisa? Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd. Okay, great. Thanks, great. Have a great day. Bye.
That was a real call you just heard. The amazing thing is the assistant can actually understand the nuances of conversation. We've been working on this technology for many years. It's called Google Duplex. It brings together all our investments over the years in natural language understanding, deep learning, text-to-speech. By the way, when we are done, the assistant can give you a confirmation notification saying your appointment has been taken care of. Let me give you another example. Let's say you want to call a restaurant, but maybe it's a small restaurant which is not easily available to book online. The call actually goes a bit differently than expected. So take a listen.
Can I hear you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people? When?
Next Wednesday at 6 p.m.
Oh, actually, we need to for like after like 5 people. For people you can come.
How long is the wait usually to be seated?
For when tomorrow or weekday or?
For next Wednesday, the 7th.
Oh no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Again, that was real.
Okay. So pretty fun stuff. So there's a couple things going on there. So there's different parts. There's what's called automatic speech recognition. So when the restaurant says something, you need to translate what they said into some form that the computer can deal with. That's automatic speech recognition. Then there's natural language processing, which is take what they said, somehow make sense of it, reason about what you're trying to do, and construct a response, usually a string of text. And then there's text-to-speech, which is I take that text and translate it into speech. And what we're going to talk about today is one part of that, which is called WaveNet. That's the text-to-speech part. And you can actually find this online. What we're going to talk about today is called WaveNets, and WaveNets is also the technology in Google's Cloud text-to-speech engine. So you can actually sort of run it right here. So you can say, so I typed it in a little earlier. I was going to do all my entire introduction to my lecture just using nothing but synthesized speech. Thought that would be too silly. So, but I thought you might like to hear it. So you just type what you want to say in here, and then you say speak it, and
Welcome to our deep learning class today. Let's get started with a prayer. Any volunteers?
Okay, and you can pick different voices, you can pick different accents, things like that. Okay, so how do they do this? I think Google's WaveNet is one of the best, most natural sounding text-to-speech engines out there. So the question is, how do they do it? And how does it compare to other kinds of text-to-speech generation? What's unique about WaveNet? So that's what we're going to talk about today. So to motivate kind of the core insight of what Google did that's special. I'd like to take you on a brief detour of audio and tell you about all the ways that people have tried to do this, or at least big classes of ways that people have tried to do this that have failed. Okay, so we're going to go on a failure detour first, and we're going to come back to, because I want you to understand why what they did is unique. Okay, so we're going to start by talking about Fourier transform. Okay, so how many of you know what Fourier transform is? Okay, so we'll just briefly review it. You have some signal in the time domain, so this is time amplitude, and you can always decompose any time domain function as decompose it as a sum of sines and cosines, where you take the sines and the cosines, you can shift them, phase shift them, and you can switch their magnitude up and down, and some weighted combination of sines and cosines will represent your original function. So here's an example decomposition. We have this original function in red, and you can decompose that in these sum of blue sines and cosines. If you add all those up together, you get the red. This is called a frequency domain decomposition, and it looks something like this. So you take a time domain signal, and you can decompose it into the frequency domain. And these little bars right here tell you how much of each sine and cosine you need in order to construct this function. And so you can convert this time domain function into a frequency domain representation, where we're showing how much of each frequency you need to construct this signal. And the reason this is useful, so imagine those graphic equalizers, like those 80s stereos where you could adjust all the different frequency levels. That's done with this. You take some time domain signal, say music, you put it through what's called this Fourier transform, which gives you the frequency domain representation, and then you can actually physically manipulate the levels, and then you can go backwards. So you can take the frequencies and recompose them into a time domain signal, and it gives you a new audio signal, but with modified spectral characteristics, like more bass. Okay? And things like so the FFT is a fast version of the Fourier transform. Okay, so yes.
So each of those marks along the axis on the F hat, right? So those are the actual frequencies, right? Like
right, and those correspond to these right here, right?
And then where does the amplitude of those come in?
That is the amplitude.
Oh,
so the height is the amount of that frequency. What's not shown, these are actually complex coefficients. So there's both a magnitude and a phase. So the amplitude tells you how much of that coefficient, and then the phase tells you how much to shift it by. Okay, so the FFT takes as input a real or complex valued signal and gives you a real or complex valued decomposition of that signal. Okay, and then we can analyze that and manipulate it in different ways. Okay, that's called the Fourier transform. And just kind of a note here, the time domain, if you look at a time domain representation, you can see all sorts of information about where peaks and valleys occur in time, but you have no indication of what the frequency content is of the signal. Similarly, in the frequency domain, you can tell, oh, there's like these different frequencies, but it doesn't tell you where in time they're localized. Yeah, here's like the math for it. It's amazing. We'll skip it. Okay, so then there's this thing called the short time Fourier transform. So the Fourier transform operates on an entire signal. The short time Fourier transform takes an entire signal, say like some awesome, I don't know, Kanye West song or something, and you take it and you chunk it in, is there such a thing? Take it and you chunk it up into little pieces, and you look at a little piece and you do a Fourier transform just on that little piece. Okay? And then you take, so that's shown here, here's the time domain. We take these little windows, we get these little windowed snippets of audio, we do an FFT, that's Fourier transform, on each one of those, and we turn it sideways. And we stack them all together, and we get an image. And that image, here actually, I'll show this one. And that image represents the time frequency plane of the signal. So you have time on the x-axis and you have frequency on the y-axis. This is showing these, this is called a spectrogram. Okay, and a spectrogram represents sort of a hybrid between the time domain and the frequency domain. And what you can see is in this particular case, there's lots of interesting structure that emerges when you look at the spectrogram. This is a spectrogram of human voice. And the spectrogram of human voice, like a human voice is actually designed to light up on a spectrogram like this. Your inner ear does something very similar to a short-time Fourier transform. You have that cochlea that wraps around, you've got all those little hair cells, and they respond to different frequencies. So your ear is actually in real time constantly doing this time frequency decomposition of signals. So what your brain sees is stuff like this streaming by. Okay, and you can see the characteristics of human voice. So you see these are harmonics. So when you speak and you say a vowel, like there's a fundamental frequency, which is down here, and then there's harmonics. And you can see how they're kind of bright here, and they're kind of dim here, but then they get brighter. Those are called formants. And you can tell which vowel is being spoken by analyzing the formants. So this might be and this might be e. It's the same fundamental frequency. In your ear, you can tell the difference, and you might be like, I can't quantify what that difference is. It just sounds different to me. It's this. Here you have a peak in these frequency ranges. Here you have a dip in those frequency ranges. And it's things like your sinus cavity and the position of your tongue that modulate these formants and creates vowels. Okay, the other thing you can see is what are called fricatives or plosives. These are sounds like they're not vocalized, so things like S's. Sounds like white noise. And that has spectral power uniformly up and down all the frequencies. Or things like those little sharp sounds that we make in English, those show up as these things. So people can actually look at these spectrograms and they can tell you what they say just by looking at them, like humans can do this. I can't do it, but you can train yourself to do it. Okay, so, but for humans, it's a little bit of a funny game. So I was going to play this little game here. Here's two different spectrograms. Any ideas about what they are? Male and female. So let's listen. And okay, maybe. I mean, I guess these are like hallelujah. How about this one? Any guesses? You too. Okay, so the point is there's no we can't look at these and essentially derive any information from them at all, but machines can. Okay. Oh yeah, quick digression. In my former life, I actually did a bunch of what's called audio source separation using directional analysis of these short-time Fourier transform things. So we would separate audio using analysis related to this. So let's give you a quick example. So here was an audio signal that we recorded using a special microphone array that we built. It's kind of fun to listen to it.
What's the score of the Red Sox game?
Okay, so two voices. If you just totally overlap, but using sort of lots of cool math stuff, you can separate that signal into two signals.
Give me directions to analog devices. What's the score of the Red Sox game?
So it's kind of interesting that you can recover the individual signals from that mixed signal. We do it using, here's some longer spectrograms. These are the spectrograms of that audio. Let's see if I can zoom in a little bit here. Okay. Okay. Anyway, you can kind of see the spectrograms here. This is an entire conversation between two people, and using technology we did a long time ago, you can split it apart into the red and the green speaker and separate it out. Okay. So the big idea. So in speech synthesis land, the way that people did a speech synthesis was in the time frequency plane. So what they did was they would take a bunch of audio signals of people, they would do a short time Fourier transform on all of them, get stuff that looked like this. They would then chunk it up into a dictionary of pieces, kind of representing the phonemes that you and I use as building blocks of language. So you have phonemes for S's and T's, and you'd have phonemes for vowels, and you'd have phonemes, stuff like that. And then they would try to build systems that would say, okay, you want to say this word, you want to say this phrase? Well, they would take the text, they would translate it into a sequence of phonemes, they would look the phonemes up in their dictionary of spectrogram pieces, take those spectrogram pieces, paste them all together, and then try to construct a time domain audio signal. The result is robotic sounding text. Never sounded natural. And you could always tell it's like terrible sounding. So Google's big idea was the following, the DeepMind. They said, let's synthesize audio directly in the time domain. So we're not going to go through all this fancy Fourier, blah, 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 blah. We're just going to generate time domain audio directly. So why has nobody thought about this before? Or rather, let's talk about this. Why is that a horrific idea? Why is that an awesome idea? What do you think?
Is this something great with phrase that you can compress to data? Like, that'd be so much, I mean, like, just wish it the time domain is a ton of data that you have.
A ton of data. Okay, right. Holy cow. Okay, so like CD quality audio is recorded at 44.1 kilohertz, which means 44.1 thousand data points per second. So if you want to generate 5 seconds worth of text, of speech, or let's say 10 seconds, let's say 10 seconds worth of speech, you have to generate 500,000 numbers. And even if you downsample that to like 16 kilohertz or something, you're still talking about thousands of data points, tens of thousands of data points per second. So time domain audio synthesis, to most people, it just sounds like a non-starter. It's like, you're crazy. Why would you think that would work? So consider this. When we thought about char RNN, and we thought about generating sentences, one character at a time, what happened to long-range dependencies? It's like essentially no structure, right? Like it's it looked great over the space of like 10 characters. So what's the audio time domain equivalent of that? Yeah, sure, like great. 10 samples of audio is going to sound awesome. But that's like a fraction of a millisecond. Like we're talking about trying to generate signals that are coherent over hundreds of thousands of samples. Okay, that's why nobody ever thought this would work. And I think that's the big contribution that kind of Google made here. They got it working, and I think that's what's impressive. And the results sound better than what anyone else was able to do. So it's kind of a double whammy. It's like, here's the world's best algorithm for generating text-to-speech. Oh, and by the way, we did it this awesome way that nobody else could. So, okay. So here are, so I wanted to play you just a few, yeah, I think that's enough. Play you a few audio samples. So this is, you can find this, by the way, on Google's blog, where they talk about WaveNet. Oh, and I'm not sure if I pointed this out, but I'm pretty sure, I've been unable to 100% confirm this, but I'm pretty sure that WaveNet is the thing that was generating the audio in that Google duplex. Yeah.
What does BCW stand for?
Parametric, concatenative, and WaveNet. So parametric is a different form of text-to-speech generation. It's where you actually try to model a vocal tract. Like you have like a glottis that sits there and generates an impulse train, and that gets modulated by sinuses and throat cavities, and then goes through all the form. Like you can frame it in terms of signal processing. And so that's another way to generate speech, that you actually simulate the physiology of speech. Concatenative is the dictionary approach, where we concatenate a bunch of snippets together. Okay, so let's listen to a couple of audio snippets.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Parametric. Concatenative.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
Okay, can you hear the robotness to that? Especially at the end, some of the intonations don't quite seem right. Here's the way that we...
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
I think it's better. Can you hear there's just a little bit of static in the background. I don't know if you listen one more time so you can hear it.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser.
And what that is since since we're generating directly in the time domain, little errors in the time domain show up as high frequency noise, and that's going to sound like white noise to us. Here's one more example, contrasting the three different approaches.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
Okay, listen to that one more time. So there's a couple things that are wrong with this. First of all, we can all tell that's just a computer. So the pauses are wrong, the intonations are wrong, and there's this robot quality to the voice, even though we can just enter.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
Okay, concatenative.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
Okay, wait a minute.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
So, better. I think it's not perfect. I think you can still hear just a little bit of, it's kind of like faces for GANs. Our human visual system is so attuned to faces, we pick up any creepiness at all. It's the uncanny valley. Same thing is true of audio. We're really, really good at listening to audio, and so the smallest weirdness sets off all these alarm bells. You can actually quantify people's opinions of these samples, of the different generated audio samples, and you can sort of see here, concatenative, parametric, WaveNet, and human speech. So human speech is still, this is called the mean opinion score, or MOS. It's a way to, you have humans essentially listen to audio and rate it in a particular way. It's kind of the standard way of measuring audio quality. And this is showing human speech is still, people can still tell the difference between human speech and WaveNet, so it's not quite there. But it's way better than the best concatenative parametric speech overall. And that's true across languages too. I thought that was interesting though that for Chinese, he's actually switched. Okay, I thought a couple more interesting, I'll just take you on a tour, just a few more results, and then we'll get into the technical details of how they do it. This is a generative model, so like GANs. If you can tell it. Normally, you would give it some speech to synthesize, but you can also just tell it to synthesize. And if you do that, you get kind of this interesting babbling effect.
Finally, like that. Periphery, so again, like Lagos is a good that, like, is it today? I pronounce James to pick up.
So it's weird. It's like, you're like, I mean, it kind of sounds like English, but you're not saying anything.
Natuurlijk zit naar ons spreken, zoals je ziet zelfs bij de lampu. Ja, ze het geen weekend, if someone's a pan.
It sounds German or something like that. Yeah.
With an Australian
really
accent.
Okay, so here's the idea. So what we want to do is we want to generate a distribution over time domain audio. So kind of GAN-like. And so what we'd like to do is, essentially, what they're going to do is they're going to say, all right, we're at time t, and I need to generate the next sample. So I want to be able to talk about a probability distribution over what the sample ought to be at time t, and I'm allowed to look at any of the previous samples that I've generated. And so that's this distribution. So that's p of xt, so this is the distribution of the sample at xt, given everything up to time t minus 1. So the model has to somehow tell us what that is. And the way that they do it is using these things called, they call it dilated causal convolutions. So you can think of this as a particular kind of neural net topology. And so here's the idea. The idea is we have a bunch of previous inputs. Sorry, so here's what a causal convolution. Causal convolutions just mean that, so when we think of convolutions, we think, okay, I've got like an image, and I've got like a little filter, and I'm going to scan the filter across the image. In the one-dimensional case, if I had an audio signal, you can imagine a little filter, and I can scan it across. Here, when you scan stuff, you just need to make sure that you don't look into the future. Because we're at time t, we're trying to generate the output at time t. Really, we can only ever look at things behind us, because those are the only things that exist. And so that's called causal. A causal convolution just means there's no cheating, you're never looking into the future. And so that's why it's sort of shifted to the left. And the point, kind of the big point of this paper was, if you just thought of convolutions directly in the time domain, and you thought of maybe a stack, like a deep stack of convolutions in the time domain, where we take what we've output before and we use it, plug it into a neural net to try to generate the new thing that we're trying to generate. If you just did normal convolutions, you need a lot of them in order to get enough context to be able to generate the new data point. It would kind of look something like this. What they do instead is this thing called a dilated convolution, which is kind of like striding in the time domain. We're going to skip a bunch of stuff. So we'll have a bunch of, and what that lets us do is it lets us, for the same computational cost, extend the receptive fields of all the neurons in our model much farther back in time. And that's what's cool about their model. So they sort of set up this almost binary tree looking thing. And sort of information is going to flow through this tree at multiple time scales. And those multiple time scales are going to combine to help generate the new audio output. Yes?
Couldn't they, like, did they try learning this?
Yeah, totally.
Kind of like, what's that model for translation? Where they're moving the focus, I guess.
Oh, an attention model. Yeah, so maybe you could do an attention thing, like transformer thing.
Yeah.
This was before Transformers came out. It's possible that those Googlers have already done that. That's not publishing it. The one issue is, remember that you have to generate hundreds of thousands or tens of thousands of samples per second. So we can't buffer a whole lot to be able to look back, and it needs to be really fast and feed forward. And so I think this architecture probably struck some sort of balance between model complexity and inference time efficiency. Just a guess though. Yeah, okay. By the way, so they had a little, sorry, I want to show you the animation. Just get to look at all my tabs. Oh, here it is. Got it. Yeah. Okay, so here's the animation. So the point was just that I thought it was useful to sort of see how this works. So you take all the previous inputs, use it to generate the next output. That becomes an input, and then you lather, rinse, repeat. Okay? And it just has to be really fast. Yeah.
So if that's the case, then where is the input with the text you want to speak?
Ah, right. So, so what they actually do is they, well, we'll talk about it. There's, they actually also condition, so they have like a kind of a pre-generator that takes the text and kind of gives you some audio, like translates it into a really rough audio, like just the fundamental frequency of the audio.
Okay.
And they use that as kind of an input to then guide this generation. Yeah. So there's kind of two halves to it. There's, the point is just, I just wanted to show how the strided convolutions extend over time. I'm sorry, the dilated convolution. So these dilated, so the advantage of the dilated convolutions is they let us look farther back in time for the same computational cost. Yes?
So then if we're at the very beginning, then those are just like 0 inputs?
Yeah, probably.
Was there actually only 3 of them?
No, I don't think so.
Would you still run with the same issue where eventually you go so far forward that if you need something really far back, you can reach it?
Yes. Yeah, so there's no, it's not like an LSTM where it can remember things arbitrarily far back. So in a sense, this is a myopic model. You're sort of relying on the text itself to give you the long-term coherence of the thoughts. Right, so we already sort of know what we want to say. Someone else has decided what coherency means at that time scale. We just need to make sure it's coherent at the low level. Okay, so one other thought that I thought was interesting was they did this. So you might think, okay, so got my context, I've got my awesome dilated convolution thing, a bunch of parameters, I've trained it somehow, but I need to get a distribution over the output of the next thing. that you can think of it as a continuous number, just the output of the audio signal at time t. And you might have thought, as I would have, that you should just like strap a Gaussian on it or something continuous, but they didn't actually do that. They actually discretized the output magnitude of the audio and did a sort of logarithmically spaced 256 bins of audio power. So that was super interesting. So I definitely would have expected them to use a continuous value thing, but discretization worked better. And let's talk about that. Why do you think that maybe it's a thing? What's the advantage of discretizing versus using a Gaussian in this case?
Removes noise.
What?
Removes noise.
Removes noise? Maybe?
And maybe just like when we talk, we don't, the volume isn't like based on some continuous scale, it's like based on what we're saying. So maybe that discretization actually reflects the
Maybe. Yeah. Yeah, it's hard to say. Another thought that I had was if you pick a Gaussian, you really only have a mean and a variance, and so you have some little continuous distribution over the output level of a sample, of an audio sample. If you discretize it though, you could represent any sort of crazy multimodal distribution. So you could have some bimodal thing, you could have a trimodal thing, and you can put probability mass anywhere you want it. And so in a sense, discretizing it, like you might think, oh, it's a continuous signal, I should take advantage of the smoothness and the continuity. But I think what they're saying is, no. You'd much rather have the flexibility of arbitrarily shaped distributions.
So I'm just thinking, like, going back to GANs, we saw that they were really good at getting small details, but not very good at like large structure.
Right.
And it seems like we're seeing with convolutions that, I mean, really the problem of text-to-speech seems like a very like small, detailed, like nuance kind of thing.
Yeah.
So what has been the success of GANs on text-to-speech?
Oh, using GANs to actually generate audio? People have tried that. I don't think it's ever worked that well. I don't know why. I'm not an expert. Yeah.
What did you show us something like that? You said there was a weird, like, gibberish babble or whatever? I thought you said that was like generated.
Today?
Yeah.
That was way back. That wasn't a GAN. Sorry, the question was, hey, GANs seem awesome. Why can't we use GANs for audio? And the answer is I don't. I think people have tried it, it hasn't worked, but I don't know why. Yeah, I don't know. Okay, a couple of other technical notes I thought were interesting. They use these things called gated activation units. In our initial experiments, we observed that this nonlinearity works significantly better than the rectified linear activation function. So this is one example where the ReLU is not the right choice. And it's just kind of this crazy, I mean, you got a 10H pointwise multiplied with sigmoid. It's like all the wrong things going on here. And somehow they did it. And then the dilated, this dilated convolution thing, the schematic that I've shown you, of course, is just a very high level schematic. What they actually have is they have this causal convolution thing, but you actually have all these layers, and you have residual connections, and some skip things. Here's their little gated activation unit. By the way, I think the reason it's called gated activation unit is the sigmoid is acting as the gate. Kind of like in an LCM, you have to forget and remember things, and sigmoids were the things that were governing that, because they either output a 1 or 0. And so this is sort of saying, do I keep the 10H or do I 0 it out? And then that goes through this 1-by-1 convolution, which learns to combine a bunch of things together, skip connections, etc. You can find the details online. But my point is just I wanted to highlight that the building blocks here are nothing that we haven't seen before. Although I thought that this was interesting. So finally, of course, what we actually want is kind of a conditional version of this, as we've talked about. Like we need to somehow get the text in there. And so what you actually want is a distribution over audio, time domain audio, given the text you want it to say. And to condition on that, you just introduce some new parameters. And you take the thing you're supposed to say, and you have some parameters like some matrices, fully connected sorts of things, and you add them together into other activations and plug them into your activation functions, and away you go. And they were doing this thing, like I said, they were doing this thing where they would condition on a rough audio signal that was generated in some other way. Although there are, so that's the local conditioning, which is telling you what to say. And then they did this global conditioning, which is things like the accent that you wanted to use. So you also need to say, hey, here's what I want you to say, and I want you to say it using a female British accent. So that's local conditioning and global conditioning. Put those together. And then that's it. So let's see, we're pretty much done. Oh, I was going to say, just really briefly, you can use this on things that aren't voice. So any sort of time domain audio could be trained on this. And so they did this thing where they trained this same model, not on human speech, but on piano music. And I thought it was really interesting. You can do the same sort of thing as with human babbling, but you can do it with piano-trained audio as well. Right? I was like, hey! So first of all, remember, it's like generating chords, progressions, runs, and of course the sound of the piano is being generated all at these pretty high frequencies. Let's listen to another one. I know. Yeah, it's good. So yeah, so it's got some very detailed stuff going on, but also some bigger stuff going on. So that was pretty compelling. Finally, you might ask, well, can I just do this on any sort of time domain signal? Like, what about text? And sort of. It didn't seem to work as well on text. And this was just, I found this somewhere online, so I'm going to try it. And what you see here is mostly proper words, but you get things like singies and truckies. So, yeah, so it's not perfect. So it sort of feels like char and or something. Right? There's clearly some local structure here, but there's no global coherence. So it doesn't text that much. Okay, we are out of time. So have a great day. We'll see you on Friday. Yeah. I love you all.